All right, gang, Math 5500. I got just complete transparency here. This is the third time I've tried to put this, create this video. Uh, for, uh, just briefly, the first time I did it, my cat jumped from, it's hard to explain, but from the chair behind me over top my head and landed in front of the computer. Pretty impressive feat, actually, I have to say. Maybe that would have been for the cat Olympics. That would be pretty competitive. But anyway, I started laughing so much and was actually startled too because I had no idea what just came over top of my head. I had to end the video, so I got to start it over. So hopefully, no cat drama in this video. All right, we're going to study. Well, we're going to revisit just briefly the estimated variance covariance matrix of B. Now, I taught this in a previous video, but I want to revisit it and put it in kind of a larger perspective down here. But remember that we can find the variance covariance structure of B by taking the mean square error times the inverse of the product of the transpose of x times x. Our focus here will be on the diagonals. Now, the off diagonal gives us the covariance. And again, this has been illustrated in a previous video, so you can rewatch it if you're still having questions or issues with that, or reach out to me and I'll try to help. But our focus is on the variances. And remember that if we take the square root of the values on the diagonals, we get the, and again, diagonals only. We don't take the square root of the covariances, the off-diagonal elements. I think I've had students do that previously. Yes, that's why I'm putting an emphasis on that here. But if we take the square root of the diagonals, it gives us the standard error, which is important for inference calculations. So not to beat a dead horse, but if we're calculating the test statistic for an estimate of B0 or B1, so if we take the test statistic for B0, we take the estimate minus the hypothesized value over the standard error for B0, not the variance, not the value that we get from the variance covariance structure. Okay, over here, same thing for B1. We would take the square root of, well, in this case, it would be this value right here. Because again, this is B0, B1, B0, B1. So this value will give me the variance for B0. This will give me the variance for B1. These off diagonal give me the covariance. Do not take the square root of this or this, any of the off diagonal elements. And again, yes, that's been done so many times previously. I'm kind of going overboard with an emphasis on not doing that. All right. So switching gears completely. Now I want to revisit the mean response and the predicted response for a new observation, and see how we handle this in matrix form. Now again, I don't get to be a professor without being in many classes. I know the nature of a student. And the nature is, why do we need to learn anything new when I already know how to do this in a really probably much simpler method, right? Well, one of the reasons is we're just trying to learn more about regression, including the theory and in this case, the underlying matrix operations that really we depend on to make these calculations. But we're building for something bigger. We're building for multiple regression where we have multiple predictors. And we're going to get into situations where we have things called dummy variables. If we have a categorical variable with more than two levels, we have to create a comparison group. We call those, and it's strange to think that they named it this, we call them dummy variables. So this is going to be a much easier tool once we get into those situations. And that's in lesson 6, so it's coming up. So anyway, if we're going to take a look at a mean response for x equals some x sub h value, we would find the predicted value, and that should be a y sub h actually. We would find the predicted value by just putting x sub h into our model. In matrix form, I'm going to introduce a column vector where x sub h is just 1 and then the value that we're making that prediction at. But we run into a slight snag here. If we try to calculate the predicted value times x sub h times b, we get something that's not defined because x sub h is a 2 by 1, b is a, that's not right, is a 2 by 1, and of course the product isn't defined. So we switch our focus to the transpose of xh. In this case, we get something that is defined. We get a 1 by 2 times a 2 by 1, which gives us the predicted value, which is a 1 by 1, of course. Now, once we define our expected value, then we focus on what's the variance look like. Well, the variance for this particular prediction is found by taking the mean square error, which is just a constant, times the product of these matrices here, which I will illustrate in R following this brief lecture. All right, so what we'll ultimately do is we'll calculate a 95% confidence interval using the body fat data set for x equal 30, xh equal 30 mid-arm. So what we're going to need is we're going to need the x sub h column vector, which we can easily create the transpose. You might say, well, why do we need both of these if we know that we use this one to make the prediction? Well, as you'll see, when we take the variance, we actually need the transpose and x sub h. So we'll just create that, and then we've got the transpose when we need it. To get the to get the confidence interval, we'll get the estimate, which will be found by calculating the predicted value. And we'll need our t-critical. And then we'll need our standard error, which we can get by taking the square root of this right here. Now, I'm not going to go into a lot of illustration. In fact, I'm not going to go into much illustration at all because they are so closely related. But if I'm doing calculating the prediction of a new observation, all of this stuff is exactly the same. The only difference is the standard error changes a little bit. The variance of the predicted is still the mean square error times this vector, this matrix, but I add 1 to it. And again, this was explained in a previous video too. But I just want you to be reminded that you add 1 to it, gives us a lot more variance. In fact, if we get pretty far away from the mean, we get actually predicted so much variation that the predicted value is oftentimes not helpful. All right, gang, let's dive in and have some fun. Take a look at R. And I've already kind of set the stage a little bit. I've created a few things. I don't really remember what I have created now. I've been interrupted so many times trying to post this video. Again, installed an old body fat, right? And I'm predicting body fat from mid-arm. So the first thing I did is create the model. Then I looked at the analysis of variance table. The reason I did that in this case was just to pull out the mean square error. Next thing I'm trying to do is create my design matrix. So I need my 1s. So that should be second nature by now. Next thing I do is create the variance-covariance structure for B. So I can see that the standard deviation for B1 is the square root of the variance for B1, which is right here. And then I come in, I don't know, I know why I did this. I just created the summary of the model that I predicted created up here to predict body fat from mid-arm to show you that the standard error for B1 matches the standard error for B1 in the table. So I didn't want you to think that I was teaching you something that was wrong. All right. Let's get into the predicted value. So now I want to switch gears. And I want to calculate the 95% confidence interval for the predicted mean fat for XH equal 30. So the first thing I'm going to need to do is I'm going to create XH, and in the spirit of always creating my matrices, or naming matrices capital, I'm going to use a cap X. All right, so I'm just going to use 130. So I know that I need 2 rows, and in column will be equal to 1. And again, I'm creating XH, not the transpose of it just yet. And by row equal false. Yeah, small matrix, not going to take up much, so I can see that I get what I want there. Now I'm going to go ahead and get my predicted value. And for this, I'm going to need beta. I don't believe I've calculated beta yet, have I? No, I haven't, so I need to do that. So. Oops. Alrighty. All right, so predicted values 14.6 and 0.99, which we saw right up here. Okay, now let's get our predicted values. So y hat, let's call it, can be found by taking transpose xh. So the predicted value is 20.67. So that's the first thing I'm going to need to calculate my confidence interval. The next thing I'm going to need is the critical value. So I'm just going to do QT. So I have 18 degrees of freedom, but I want, again, I have a 95% confidence interval. So if I visualize that center 95%, I'm missing 5%. Half of that needs to go to the left, 2.5%. Half of it needs to go on the right tail, 2.5%. So I need the value that has 2.5% below it from the t-distribution degrees of freedom 18. So that's negative 2.100922. Now the next thing I need to do is I need to calculate the variance for the predicted value. So I'm going to do variance YH. So I need the mean square error, which let me make sure I did that above. I'm pretty sure I did. Yeah, mean square error. Now, guys, notice that that's not a vector. It's not a matrix. So I don't use the percentage multiplication sign percentage. I just use just multiply because again it's just a constant. So now I'm going to need the transpose of XH, and I need make sure I get everything correct here. Okay, so I have the pieces of the puzzle, right, that I need. So calculate lower bound of 95% CI for the predicted mean body fat for XH equal 30 for the mid-arm. So I've got my predicted, which is YH, minus, so I have, what was the T critical? 2.100922 times the standard error for YH. So our interval would be 17.7 to 23.6, the predicted value. Now, just illustration, the only modification for predicting YH, well, body fat, for a new observation is the following. All I'd really need to do is go back up and get this. Add a 1 there. And I get the variance for the predict. Everything else is exactly the same. So I'm not going to waste your time. Well, it wouldn't be a waste of time. I'm just not going to go into that because I know you can handle that. So I don't think there's much else to cover. So this actually ends lesson number 5. So lesson 6 we move into some really cool stuff. I think lesson 5 is really cool too because it sets the foundation. But we move into multiple regression in lesson 6, which is super cool. Take care.